One of the interesting challenges that the shuttle and the station have taught us as operators is, and in fact I think it's a challenge for system engineering of programs, is what is a program life? The shuttle was, as a program and as an operation, intended to be open-ended with, okay, yeah, we had some spec limits on the hardware that we'll have to go recertify, but you know, geez, we're flying B-52s and we figured out how to do that. Some very interesting lessons learned that particularly the Columbia have highlighted is that all of us tend to believe that these things will last forever. And one of the lessons of Columbia was we were blinded to the aging aircraft thing, which the Department of Defense lives. We'd never had a spacecraft that flew for longer than, I don't know, 4 or 5 years. I guess the Apollo flew from the 67 time frame through the end of Skylab, which was 74, and then one last hurrah in the Apollo-Soyuz test project. The shuttle, it had a spec life, and we've gone long beyond it. We haven't gotten anywhere close to the number of missions, but the calendar life we exceeded. The International Space Station, it was, when things rolled out of the factory, they expected to be, they had a design lifetime. Well, some of them spent 2/3 of their design lifetime on the ground waiting to get launched. So, one of the things that we have had to grapple with in the shuttle is it was spec'd at so many years, we flew it for many years beyond that at a lower flight rate, was we had to try to architect an operation that would last for a very long period of time, but with the idea that, well, it does have a fixed life and we'll go on to Shuttle 2 and we can fix things then. Well, a lot of the things we would have, Shuttle 2 was a metaphor, an idea that, well, when the shuttle gets beyond its design lifetime, we'll build an upgraded, better, bigger, more efficient one. Well, we never did all of those things. And so the program constantly struggled with recertification from lifetime, the fact that we never got to the target number of flights per vehicle, but we vastly exceeded the calendar lifetime, that the vendors are no longer there, or in some cases the government has to pay them to do things that don't at all advance the national competitiveness, and say, no, keep building that crappy old thing because we can't afford to do an upgrade. Or, as in some cases, we did upgrades. We upgraded the cockpit once, and we're contemplating updating it again. Good and bad. If you can retire stuff that you can no longer afford to find spares for, that's really good. But that becomes a transition in the operation. You either force it to look exactly like the old, you force the new digital thing to look exactly like the old mechanical thing, or you go through a re-engineering cycle to change the nature of the operation. And this is one of the things that I think about a lot in our constellation preparation is, to a very large extent, the amount of things that changed the way the shuttle operated were very, very few. And so the fear I have about following the shuttle methodology for constellation is we say, well, we're going to engineer the perfect operation around a stable knowledge and try to pound it into repeatable grooves. That was our mantra after the orbital flight test of the shuttle is, okay, huge complicated thing, let's try to beat it into repeatable grooves, don't try to do too much different with each mission. Never worked, and so we're kind of on the bad end of both trades, that we had tried to architect a stable recurring thing, and the vehicles didn't change as much as we wanted and didn't change as much as we needed. If you're trying to get to that recurring operational vehicle, you have to simplify, standardize, and every bit of knowledge that the operator has to have, you have to stabilize and be able to transfer it to the future operators. Apollo didn't have any of that. I mean, I'm tickled we did the lessons learned reports from Apollo, but again, some of that was we needed work for the people to do before the next program geared up. And the people who flew Apollo were the heroes of Gemini. People who flew the early phases of Shuttle were the heroes of Apollo. And so, happily for us kids that came in at the end of that, many of them were good teachers, but not all of them were. And you can't write some of this stuff down. So there's a whole skill of transferring methodologies. You know, I count that I had 3 great teachers, one of whom was an old Rockwell engineer who took the time to teach me how to think through a system problem. Operations is about finding a way to execute the mission and execute it within the constraints and the capabilities of the vehicle. There's a view that all ops guys are just a bunch of cowboys going off doing what their thing, but fundamentally our methodology is to understand the mission requirements and understand the constraints, and there's constraints in a lot of forms. Some are do not operate this equipment beyond this performance parameter because it's not certified beyond there, or we know for a fact something horrible will happen. And so that is design characteristic data that is translated either through documented constraints into flight rules into procedures, or where it's a hazard control through the formal documentation of the hazard controls that are assigned to mission operations to execute. The shuttle is an incredibly flexible and incredibly complex data with an incredibly complex set of constraints. It's also, in virtually all of the missions, particularly the space station assembly missions, it's being operated to the maximum capability that it has. This is very different from the way the shuttle was contemplated as you look at it in the late 70s, where, well, we're going to fly 60 flights a year, and if a mission don't work, no big deal, just throw up your hands, kind of safe everything, come home, figure out what happens, and go up next week and finish the job. And of course, we built operational plans to figure out how you fly that, and it was kind of FAA with a couple engineers who could say, gee, you know, that does look bad, maybe we ought to come home. Basically help the flight rules fly. Particularly on the assembly missions, we are operating the shuttle to every inch of its mass to orbit. That puts a lot of constraints on how the mission unique ascent design is done, the whole robotic operations and the loads back into the shuttle. You know, the shuttle was designed to take little things out of its payload bay and hand off. Well, here we have something heavier than the shuttle, the station, and we sometimes use the arm to interact with that. Well, that's more than we do amazing things with robotics, but it all has to be very carefully designed through these constraints. And so if you're resource constraint and margin poor, you have to do a lot more work to convince yourself that the mission that you're going to execute will work, and you have to trade many things within the mission. The goal everybody I know in the program has is, no, we want to have lots of performance margin in these vehicles. We don't want to have to do a rich optimization of each mission that leads to, in Shuttle today, we've got 200 people who do recurring mission trajectory flight design. The idea is, no, the vehicle should kind of figure all that stuff out on its own, and if we have lots of ascent performance margin and lots of performance margin on the the rendezvous instrumentation and all of that. Well, yeah, we just go do it. We do a few checks on the plan to make sure it doesn't violate a small set of criteria, and that ideally we wouldn't have a lot of mission variation in that. That's kind of the risk, and the shuttle was as bad as it was, or as wonderful as it was. You can look at it two sides of the same coin, because we found we could do all kinds of things with it. And okay, it didn't carry 65,000 pounds of cargo to orbit, but it was a horrible day when the Freedom program figured that out after designing in bigger chunks. This is a spectrum that is a huge driver to the nature of the operation. And it is, I have feared that there was a risk that everyone looking at, no, we're talking how a 777 flies. I think we're over that. But the complexity of the constraints and the scope of the operational hazard controls, that drives everything. If, on the other hand, the crew is having to manually pilot to the entry attitude and assure that they're in the right attitude at the right time before we fire the retro rockets, or whatever we'll call them, or during the flying in approach to dock to the other Constellation spacecraft to go to the moon or the station, well, okay, you have to have higher functionality. And if you want to increase your level of mission success, you have to train the crew to be smart participants in this and say, well, okay, I've violated the red line there, but it's okay in this case because. And we rely on that kind of skill. The notion is we haven't, as we learn these vehicles, we'll be able to put that stuff into automation and into the standard things that the crews learn and their capability, but we have saved failed missions time and time again by having the crew, sophistication in the crew and sophistication in the ground team. And the more we can make like when we go to the moon, the crew has to be relatively autonomous, because when you go to Mars, there isn't, I forget the alarm like it happened in the moon. The crew has to make every possible decision because, you know, they'll send an email on how it went rather than have a dialogue about is it okay to land. So this is one of the things we have to get to, is true crew autonomy if we're going to go to Mars. And that's a very scary thing for programs and crews and us on the ground. So it's a big transformation we're going to have to go through. And this is, what does it take to make you comfortable that we have automated enough and trained the crew enough that they can do everything they need? Yes, the shuttle today is set up that the crew can do those kind of things by themselves, but we have the crutch of a bunch of smart people looking at it on the ground, and if it looks a little different, we can get a pretty quick answer. That is a huge step. We've never built a vehicle that was in my mind, sufficiently autonomous. Station has a requirement that says the vehicle shall be able, the crew in the vehicle shall be fine for a 24-hour period after any event. Except it's not that way today because it requires the full redundancy at assembly complete, and I bet you it won't be there then. So there's this whole thing. I think there's a risk that both us and as operators and the designers will get into a comfort zone about, well, we know how to build this, we'll build it that way, and we will put off that revolution we have to exercise when the crew goes to Mars and they literally are on their own with what their little machine can do to help them.